So as I mentioned last time, this is the first of two, it's really three lectures on two different interesting topics that I think you would find helpful to understand, and unfortunately it's a little bit beyond the level of sophistication of Pintos. So it's something that you won't learn from Pintos unless you decided to do a project like a CS81 project or something like that after this class is over, where you decide to add something to Pintos or something like that. So, but what we're going to talk about today is how signals work. Basically, I think we're all basically familiar with signals. It's something that you got exposed to a little bit in CS24, but basically this is just exceptional control flow or interrupt-like control flow for user processes exposed by the kernel to user processes. Some of the hardware interrupts are mapped into signals, and other interprocess communication mechanisms are also sort of passed along using signals. So you can register a signal handler if you like. There were a couple of different ways you could do this. The easy way is to have this SIGT type, which is defined in the UNIX standard, takes an int indicating the type of signal and then returns nothing. And so you could have one signal handler that handles a bunch of different kinds of signals. Tends not to be the way that it's done, but it's certainly possible. Okay, so that's the thing, and then you have the signal. This is a system call. And the system call takes a function pointer for the user process and what signal you want to handle with that function, and it returns the previous signal handler, which may be something also like SIGIGN or SIGDFL if you're replacing the default behavior, something like that. So straightforward system call that registers it with the kernel, and so this is all in signal.h. Here was the example that we looked at in CS24. So we have main, we register a SIGINT, remember that's control C, and SIGAlarm is just the timer alarm mechanism. The timer is used by the kernel to do preemption, so that's why it's guarded, so we're not allowed to manipulate it directly. But this is also exposed into user processes using a number of APIs. Sleep is another example. You guys are implementing Sleep, or hopefully have long ago by now, and a few other facilities like that. So we say I'd like to get a SIGAlarm in 1 second, and then we have these two signal handlers, one that prints hello and then requests another alarm in a second, and SIGINT, which taunts the user. And if you remember CS24, if you hit Control C, then this will definitely taunt the user, but if you do something like Control / or Control D or Control M or a number of other things, then that'll easily shut this program down because it only handles SIGINT. It doesn't. There's a few other signals that you would have to trap as well. And then you always have your SIGCHLD, I think it is, that is the big gun if you really need to stop the process from running. So, and you can't really register a handler for that. Okay, so this is the idea. Any questions about the mechanism? Just make sure that this is the starting point. It turns out that there's another more advanced signal handling mechanism called sigaction. So signal is the simple one. Sigaction, notice you have a signal number, and instead of just specifying a single signal handler function pointer, you can actually fill out this struct that describes all kinds of details about how you want to handle the signal, including like, do you want a separate stack? Do you want signal delivery to be overlapping, or do you want it to be sequential so that no two signals overlap? Things like that. And notice that you have a sigaction for passing in details and then a sigaction for receiving the details of the previous signal handler. Okay, so there's a lot of different things in there. You can either have just a simple handler, or you can register a handler that takes 3 arguments. The 3-argument one is way more interesting than the 1-argument one. Basically because you have a SIGINFO struct that describes the details of the signal. And we use this in assignment 8 on CS24, where we do that weird pretend paging system using SIGSEGVs, segmentation violation signals. And we can actually find out the address that triggered a particular seg fault. We can find out if it was a read or a write or things like that. So you actually get a lot of interesting detail in that siginfo struct. And then even more interestingly is the memory context. Okay, so you have that ctxt pointer. So this thing is this weirdly defined U context, and that is, on many platforms, they kind of want you to treat it as a black box because it does depend on the OS. It depends on the OS and it depends on the processor. This basically contains all the CPU state of your process. So in the signal handler, you can look at, well, what was the RIP or the EIP of the interrupted code? What was the register state at that point? What's the stack pointer? You can get all that stuff out of this machine context. Okay? And like I say here, you can use this to implement user space threading. That's what we do in assignment 7 in CS24. We use this function to implement context switches between user space threads and preemption. So pretty dang powerful. I mean, it's a really neat mechanism. And you could do this on the Mac as well. Like, it's not hard to implement user space threading on a Mac, but the machine context completely changes specification. Or at least it really did before when it was on PowerPC. But now that we're on Intel, at least all the same things will be there, but they may be in different positions in the machine context. So a little bit challenging, but definitely fun things you can do with it. So there are bit vectors for each process. Again, we talk about this in 24, so this is mainly review. Basically, there's a blocked bit vector and a pending bit vector. And the pending vector says what needs to be delivered. Blocked says what am I not interested in receiving. Oops, wrong button. So yeah, pending bit vector, what needs to be delivered. And the important detail about this is that there's 1 bit per signal type. And so if 2 of those signals occur, I only know that that signal type needs to be returned. I don't know that there's 2 of them. Okay? So this kind of will swallow multiple events of the same type if they don't get handled quickly. That's just one characteristic of this system. You may say, why in the world would that be? And it turns out that this is the way the hardware interrupt mechanism works as well. So it's funny because this does expose, in a very simple, clean way, exactly what the hardware is doing. Okay, then you have the blocked bit vector, which same thing, there's 1 bit per signal type, and basically it allows you to say, I don't want this kind of signal to be delivered at the moment. And what's neat is that when you go into the signal handler for a particular signal type, the block bit gets set automatically, so that that signal type won't be delivered again while we're already in the handler for that signal type. Okay? So that means you can definitely have a signal that's blocked and pending. Okay, that's easy to have happen. Okay, and this is what I was just describing. So this is all review. This is all basically what we talk about in CS24. But the question is, how do we actually implement this kind of functionality? And we're going to look at Linux as a sketch for how this can be built. And you'll start to see, wow, this implementation is actually quite clever and gives us a lot of benefit and capability with a very clever design. Okay, so when is a signal delivered? So these are all the kinds of questions we want to understand. What if the process is running? What if it's ready? What if it's blocked? How does signal handling affect scheduling? If I have multiple signals pending, how does the kernel take care of this? Okay, and there's one aspect of this that we're totally ignoring, which is basically multi-threaded programs. So you're using POSIX threads or something like that. It turns out that POSIX threads complicate everything. I mean, it's nice to have multi-threaded programs. You can take advantage of multiple cores. But the issue with signals and multi-threading is that if you don't specify anything, that signal might be delivered on any of those threads. So then what do you do? And what many programs that have to deal with this issue do is they set it up so that one thread handles all the signals. And so they block signal delivery on all the other threads that actually want to do computation, and then that one thread deals with it. And that simplifies the problem greatly. But you have to, we're completely ignoring those kinds of issues. Okay, processes may or may not be running when a signal is dispatched. I'm just going to use that term right now to describe the process. So you can imagine it could be running. I touch memory that I shouldn't touch, and I generate a fault, and the kernel passes that to me as a signal. But it may also be that, another good one would be divide by 0. If I decide to divide by 0, that generates a signal. But it may be that some other process is running. So they send me a signal using kill, or a child process terminates, or somebody in the console hits Control Z, and that causes a sig stop or a sig t stop to be sent to the process. So there could be a lot of different things that are going on. And so the signal mechanism distinguishes between generating the signal and delivering the signal. And it's a really nice, clean way of thinking about this, because you can see that all of these examples that I give up here on the slide, they really are talking about generating a signal. I need to register that a signal needs to be delivered to a particular process. Okay? So the kernel goes in and updates the data structures. Remember, it's the whole thing of the kernel just being a sophisticated bookkeeper. It goes in and records that a signal needs to be delivered to a particular process. Okay? The process is not ready to receive it yet. That's delivery. So we're just generating the signal right now. Sometime later, the kernel says, all right, it's definitely time for this process to deal with this signal. And so it will, for example, invoke a signal handler if the user provided one, or it'll perform the default behavior. Okay? And so there's some separation. There's oftentimes separation between signal generation and signal delivery. Okay? So that's the way to think about it. That generation does one set of actions. Delivery, honestly, delivery is the complicated part. Okay, so we mentioned pending and blocked. Those are easy. Remember, they just record on a per type of signal basis whether or not a signal needs to be delivered and whether it can be delivered right now. But there's also a bunch of other machinery that Linux at least uses to keep track of signals. Okay, you can see that there's a collection of signal handlers so that we know what should we do. And there are default values for some of these things. Remember, there's sigdfl, which says do the default thing, and sigign, which just means ignore this signal type. Okay? So that's all stored in there, but then you also have this linked list of what signals need to be delivered. Okay? And this would be the kind of information that goes into siginfo. You remember that that's, the more advanced signal handler can receive a struct describing what exactly happened, so you can store those details in there. Clearly, it's not going to fit in a bit of a bit vector. So we need a place to store that. Okay? So that's an important detail. There's also another thing. So I already talked about that. The one detail that you may find comforting is that there's a new kind of signal type, new like the last couple decades, but they're called real-time signals. And those you actually record every single instance or every single occurrence of a particular signal type. So whereas the default set of signals that we're used to working with, you just know that at least one of those events has occurred. There are other higher resource requirement signal types that will actually get, every single one will get logged if you need to do real-time kind of signal handling. Okay, so generate a signal. So somebody sends a signal to a process. Maybe it's because of that process's behavior, so in that case it's the kernel, or maybe it's another process. Basically, there's a function that manages all these data structures. Okay? And like I say here on the slide, in Linux 2.6, it would be specific send siginfo. Okay? And so depending on the circumstance, for example, the signal type, if we already see that there's a pending signal of the type, well, we can just ignore the new signal. So SIGCHLD occurs. Okay, so you mark the bit in pending, and then another SIGCHLD occurs. Okay, we don't care. The bit's already set. Now, like I was saying, real-time signals will ignore that mechanism because you want to have every one of those delivered. Okay? If the process is ignoring the signal, so again, how does it determine that? It looks in sighand, looks in the array for the signal type, and the signal entry says sigaction. Then it just ignores it. Okay, so that's fine. We're all good. Yeah, I should also mention that there's a few other interesting details that can occur here. Like, again, has anybody hit like Control Z to put something in the background It's one of these things that you can do on Linux. It's really nice. You can do it on Mac too. Any Unix type platform can support this. So that basically is implemented by sending a sig stop or a sig t stop to the process. Well, if you send a sig stop and then immediately follow with a sig cont, continue, then those two signals cancel each other out. So you have a few situations like that that are also resolved in this stuff. Like if you are sending a signal and it's already canceled, or it cancels another signal that's already in the queue for that process, then those things sort of mutually destroy. Okay? So you have a few other little rules that have to be implemented. It's not complicated. Anyway, the new signal is added to the signal queue. And here's the thing that's fun. If the process was blocked, well, it doesn't need to be blocked anymore because it can actually do something if it got the processor. Okay? So basically it moves to the ready state. And same thing with suspended. If it was suspended, well, if it got a signal, then it needs to react to that somehow. So it'll be moved to the ready state. Okay? Yeah, and so this is basically just talking about what... that's not entirely true. This isn't talking exactly about what I was talking about. But like it says here, there are a few signal types that are not added to the signal queue. SIGCHLD is a notable example. When you send SIGCHLD, basically you're saying, I don't want to schedule this process anymore. I want to just go straight to termination. So you can see that these signals will be enforced by the kernel. The next time the process is up, then the kernel will go ahead and enforce the result of that signal being delivered. Okay, but we'll talk about that. The only detail here is just that it's not added to the list of signal details. Okay, any questions about generation? Pretty easy, right? I mean, all of this is just bookkeeping, and I would imagine that all of it follows exactly what you would expect it ought to do. Okay, now delivery. This is where it gets more interesting. Signals basically are only delivered to a process that has the CPU. That should make, again, total sense because either the kernel is acting on behalf of the process in delivering the signal, or the process has registered a signal handler and needs to respond in some custom way to the signal being delivered. Okay? So that makes sense. We need to have a process that's running. Now, the way that this happens is as you would expect. For some reason, the kernel scheduler says it's time to run process whatever. And on its way out to the process, it says, do you have any signals that need to be delivered? And if there are, then it goes ahead and handles them. So you can see that this is sort of the last step as we're leaving the kernel, going back to the process that was just scheduled. We're saying it needs to handle signals, so we'll go ahead and take care of that right at the end. At least that part makes total sense. Okay, so how can we handle the signal? Well, there's two ways, and you kind of, well, this is expanding the handle signals part of this question. Okay, we either ignore it or do the default action, and that's easy enough. All of this is handled inside the kernel, so that can stay on the kernel side of the dotted line. The other option is that we have a user mode handler. Okay? So that's the other possible resolution that we have. Okay? Pretty obvious. So this is the more complicated flow. So all we've really done to this diagram is added the kernel handle signal question. And you'll notice that if it's a kernel handled signal, we handle it and then check if there's more. Okay? And so we actually have a loop where we can consume as many signals as possible if they're kernel handled. Otherwise, if it's a user process handled signal, then we have to switch to user mode, invoke the signal handler, and then we do this one little step back into the kernel and back to the user process. You'll see why momentarily. Okay. So this is basically how the flow works. And does it really matter that we didn't get to all the signals? Well, not really, because at some point we'll context switch away from the process. Maybe it'll do some slow operation. Maybe it'll get preempted. But something's going to happen to kick that process off the CPU. And eventually, when we go back to it, we can deliver the next signal. Okay, so you can see that there may be a little bit of latency here. And this is another one of those kinds of things that you can configure when you register a signal handler, like how quickly do you need to know about the signal. Okay, so there's some things that you can control with that. Again, Linux 2.6, which is woefully out of date by now, there's a doSignal function that actually implements this specific logic. Okay? And like I say here, the code has been restructured. I think the important thing to keep in mind is how is this built? Like how is this mechanism constructed? Because to me, that's the interesting part of this. I can't tell you, for example, if the current kernel handler is able to do multiple signals delivered in rapid fire or not. I can't really tell you that off the top of my head. But you can imagine that it would just be a variation on this mechanism. Once you understand the implementation, you can tweak it however you want. Okay, delivery challenges. So here's the fun thing. I say here the signal handler has to return back to the kernel so that the user process context can be restored. You might have to take my word for that at the moment. But if you think about it, I was running some code in the process. Then a signal happened. And I didn't know about it because that generation mechanism is separate. But then it needs to be delivered. So I need to interrupt whatever part of the program is running so that I can run the signal handler. Okay? Signals can interrupt system calls. If I have a preemptible kernel and I'm in the middle of a read or a write, well, a signal can come in while that read is blocked or while data is being moved or something like that, and that signal will interrupt that system call. Some system calls specify that when interrupts occur during that system call, that they need to return EINTR or something like that, or minus EINTR. So somehow the system call has to find out that the signal happened. Okay. Handlers can make system calls. Okay, so that's an interesting one. Somehow we need to make sure that we can invoke the system call handler. We can trap into the kernel from the signal handler and get back to the signal handler. And finally, signals can long jump out of the signal handler, which is crazy talk. Okay. So the question is, does long jumping out of the signal handlers mess up this mechanism? Does it gum things up? So these are some of the challenges that the signal delivery mechanism has to resolve. Okay, and you could probably come up with a few others, but those are the big ones as far as I can tell. Okay, so we have a loop. Basically, doSignal tries to see what signals may need to be delivered. Okay, and again, so we had the cancellation mechanism that I described briefly on the signal generation side. Well, this also applies in the signal delivery side, depending on how things are passed to the process. So if you have a few signals that cancel each other, then the doSignal implementation just deals with it. Okay? Otherwise, it may go through and figure out what signals need to be handled, and it'll look for what satisfies its needs. If there's nothing else, no biggie, right? Pending signals, no, we just drop down to the dispatcher. Remember, that restores or actually, we're kind of doing an IRET, right? So we restore the machine context back to the user process. We IRET, or we sysleave, or sysexit, and that's going to transition back to user mode. Okay, so we're back in user space, no biggie. But if we have a pending signal, then we remove it from the pending queue. And this is kind of an important detail. So we're in the pending signals yes line, so that little short line. Basically what we do is the kernel updates the process to say, okay, I'm dealing with this signal, so remove it from the queue and clear the pending bit. And so that actually happens before we even deliver the signal to the process. We record that we're handling it, that it's not going to be a problem anymore. Okay, so if the signal is being ignored, great, we can ignore it. Okay, and again, this is one of those things where, what if a signal was generated, and at that point it wasn't being ignored, but then the process said, actually, I want to ignore that signal, but it was still queued. So the doSignal has to deal with that situation. So you can imagine these little race conditions that could occur. So ignorable signals, though, we deal with them right away. Deal with them by ignoring them. It's easy. Okay, next it looks at the default action. Okay, and like I say here, what we're assuming is that the action is set to the default action, and the default action is not to ignore it. Okay, then doSignal will go ahead and carry it out. And I want you to look at these default actions. Okay. So default actions are terminate, dump, which includes terminating, ignore, which we said is handled earlier, stop, and continue. And notice that all of these pretty much dictate the scheduling characteristics or life cycle characteristics of the process. None of them really involve talking to the process itself. Okay? None of them involve running user code. So you can see that these are all actions that the kernel can carry out itself without involving the process. So that's why they can be done on the kernel side of the fence. Okay? So let's say all of those things are not appropriate for the signal that's being delivered. So we're assuming not ignorable, not a default behavior. The user process has registered a signal handler for the signal. So now we need to go ahead and get the user process involved. Okay? This is the state of the stack. I use the term stacks plural because there are multiple stacks involved at this point. Remember, we're inside the kernel because we're getting ready to go back to that user process. So we have whatever, starting at the bottom, other kernel stack data. So this may be function contexts and so forth. Stack frames that are generated from function invocation. Then we end up with all this stuff from either trapping or interrupting into the kernel for the process. So we have the register state of the interrupted process saved by the interrupt dispatcher for the OS, interrupt number, error code, or a dummy error code, depending on the situation. And then the top boxes are all pushed by the interrupt dispatch. So the CPU is putting those things on. EIP and the code segment, current E flags, or I should say E flags before the interrupt was dispatched, ESP and SS that point to the stack of the user process. Okay? And the user process was doing something, so it's got stuff on its stack as well. We don't know, we don't really care. Okay? So that's the current status of things. So what do we do to get the signal handler to run? Well, like I say on the slide, it's really easy. We have the machine context of the interrupted process, and we can manipulate it because we're the kernel. And when we go back to the process, we will restore that stuff, and we'll just end up in the signal handler. So we could just plop in RIP or EIP, whichever bit width you're working with, just put in the signal handler address. And bang, now we're running it. Okay? So that's nice, except for the fact that we need to remember what code was interrupted by the signal. So we can't just go and change the machine context without remembering the original version of it. Because we need to be able to, once the signal handler exits, we need to be able to get back to the code that was interrupted. Okay? So like I say here, we can't just overwrite the previous CPU state. Okay. So we have to set up another context. And so this is where it starts to get a little bit sophisticated. Okay? Now here's the next issue. We know we need to have another CPU context so the signal handler can go back to the process. But the other challenge that we have is when we return back to the user process, what's going to be the state of the kernel stack? Because remember, we're going to return from function, so the other kernel stack data goes away. We're going to, the dispatcher, the scheduler dispatcher is going to restore the machine context, so all that stuff's going to be consumed. And then we're going to IRET, or we're going to leave, or whatever the appropriate instruction is to get back to the user process. So that's going to take away the topmost stuff. So basically, the kernel thread stack is going to end up completely empty. So doSignal, or whatever the analog is on OS X or whatever, will go ahead and copy some machine context details to the user process stack. Because it knows that'll be there even in the signal handler. Okay, so like I said here, the CPU context of the process before it was interrupted by the signal will go there. And other details for dealing with signal handler invocation. Okay. You'll see some of those details as we go through this. Okay. So these are used when we go back from the signal handler to where the process was interrupted. Okay. Now the kernel is able to set EIP or RIP to the address of the signal handler. Okay, everybody see that? So nice, straightforward, clean mechanism. We copy the details that are needed after the signal handler to the user stack, and then we change the kernel thread stack machine context to go to the signal handler. Okay, so now we need to set up, because the signal handler is a C function, we need to satisfy its calling convention. So basically, that's what we're talking about now. DoSignal will go through and set up the stack frame for the signal handler. If we have one argument, well, we just push the signal number. If we have the 3-argument version, we push other details onto the stack. Okay. And so that's set up. And you'll notice what's neat about this is, remember, we already saved the machine context of the interrupted process onto the user process stack. Well, if we have the version of the signal handler that wants that machine context, well, now it's really easy because we just have a pointer to where we saved it on the stack. Okay? And since it's in user space, the user process can manipulate it. So boom, now we can easily build user threading libraries and so forth. It's really straightforward to do this stuff. Okay? I should ask, are there any questions, or is everybody following along? It's a pretty neat mechanism. Okay, we've already gotten the ability to manipulate the machine context. We've given that to the user process if it wants to, simply by copying that context to the user process stack before we do our signal dispatch. Okay, last thing for the stack frame. There is one thing missing from the stack frame, and this is one of those things where if you took CS24 last year, well, even then you should know what is still needed. But what's at the end of the signal handler? A return statement of some kind, presumably, right? So, when it returns, where does it go? Well, we need to have some details on the user process stack to make sure that when the signal handler returns, it knows where to go. So that's the last detail missing from the stack frame. So this is where it becomes interesting because you notice that we have the register state of the interrupted process. That is on the user stack. We kind of need to get back to the kernel so that it can restore that interrupted process context. And you might say, well, why? I could do that just all in user mode. I could just restore the registers and so forth. And you could, but remember that the interrupted code may have been running a system call that needs to now say EINTR, or it needs to say some other thing. So we kind of need to get back to the kernel just in case that signal delivery interrupted something inside the kernel that the kernel was doing on behalf of the process. So we have to get back to the kernel. So basically, there is a special system call. You probably never heard of it, and you could run man on it to see what in the world this is. But there's a special system call called sigreturn. And all it is a little entry point to get back to the kernel after a signal handler completes. And so there's a little bit of code somewhere in user space that says invoke the sysreturn system call and then do an int 80 or what is it, syscall or sysenter or something like that. I just need to do the sysreturn stuff. Okay? And sigreturn, basically, all it does is it cleans up that stack and restores the process context. And if a system call was interrupted, it carries out the appropriate action. That's basically all that sigreturn does. Okay? That's kind of like the one wart on this, and it's not too bad. Basically, nobody knows about this unless they dig into how signals work. Okay, any questions about that? Hopefully it's all clear. Now, we've modified the user stack, and so you can see that the details on the kernel stack now do not correspond to the new state of the user process stack, so we have to modify that. so that when we iret back or we sysleave back, we restore the stack pointer correctly. And now doSignal is done. So it returns to its caller. Notice stuff starts disappearing off the kernel stack. The kernel stack ends up empty, and we transition back to the user process and start running the signal handler. Okay? Pretty straightforward, I think. And the nice thing is it can make system calls without any problems because we have safely stowed away the interrupted process's context. The kernel is left in a good state. I mean, if it's a well-implemented kernel, it won't be a problem. And so the signal handler can do whatever it needs to do without causing any problems. Okay? Now, again, we're assuming that the signal handler is implemented properly reentrantly. Like, we're not going to have a call in our main program that calls malloc, for example, and then the signal handler also calling malloc because that's a poorly implemented program. Okay? That's a recipe for disaster, in fact. If you want to seg fault really quickly, then or at random times, you can do that. Okay, so this is the state now. Signal handler has run. It's done its thing. And now we invoke the sysreturn system call. Okay? The kernel stack is empty until we trap into the kernel. Then it starts getting populated with details. Okay? Remember how this all works. Okay? We're assuming the int mechanism, but sysENTR or syscall have similar details that they go ahead and set up. Okay? So the kernel thread stack now contains the user process details. And remember, this is the register state of the signal handler, not the interrupted process. So all sysreturn does is copy the CPU context of the interrupted process back into the kernel stack so that now when we return, the next time this process gets scheduled and we go back to the process, we will restore the interrupted process's context. Okay? And like I say here, this will include any changes that the user process may have made. So if we have the advanced signal handler and they manipulated useCTXT, so they access the interrupted process's context, those changes will also be restored. Okay? So the kernel is carrying out things on behalf of the process. Okay? Then sysreturn cleans up the rest of the stack so that we're back to where we should be, and it returns to the user process, and that causes the process to pick up where it left off. Okay? Easy. So we've gotten to the signal handler, we've done the signal stuff, then we've gotten back to where it was interrupted, and we've carried on with our normal work. Okay? Does it make sense? Now, the last detail of this, or I should not say the last detail, it's the second to last detail, really, is that we may have a situation where a system call is interrupted. Okay? Good coffee. So, in this case, basically what happens is, like I said, there's many system calls that need to indicate that they were interrupted, and there's a special error code called EINTR that is returned in those situations. Okay? Like sleep is a really good example. If you sleep for a certain amount of time or nano sleep for a certain amount of time, then those calls are defined to return back to you and say, you were interrupted while you were sleeping, and this is how much time you actually slept. So that's one of the examples there. You can see it too on read and write and a few others as well. So you do see that sometimes. And remember that since you have a situation where you were in a syscall and then a signal was delivered and now the signal handler may make syscalls, that's another reason why the original syscall may say, hey, I was interrupted by something else. Because it may be that it wasn't completed properly. Okay. So you have some syscalls, they can be restarted, which is really dang clever, honestly. It's pretty cool. And some must say, I was interrupted. Okay, so if we're in a system call, the thing that's interesting about it is that we're already going to be inside the kernel because the kernel is doing something on behalf of the process. It's a syscall, right? So inside here, you're going to see that the interrupt is set to something. Okay? Think about what all that doSignal call does inside the kernel. It's got access to the machine context of the interrupted process, so it can say, hey, the interrupt that was occurring was int 80 hex. So it'll say, you were inside the kernel when that signal went off. Okay? And so it can look at that and say, all right, well, then I can deal with this. Okay? So basically, the signal delivery mechanism can inspect the process state and see, they were inside of a system call. Okay? So basically, the kernel can do one of two things. One is modify the process's machine context to record that the system call was interrupted. And that's pretty easy to do because remember, EAX or REX is going to be the return value. And so it just sets that register to -EINTR. And then it says, okay, it's time to go back. What can we do, right? And so the process, when it gets the, when the kernel returns from the trap, it'll look at EAX or REX and say, oh, I was interrupted. Okay, so it can retry it. And that's one of the things about systems programming is if you see an interrupted system call, you need to retry it. And this is one of the things, I don't require you guys to do that for anything really, because we don't do systems programming at that level. But that's what you'd have to do. Now the second option, which is wild, because like I said, a few of these system calls can actually be restarted. How do I restart it? Well, you go into the machine context of the interrupted process and just make it do the trap again. So the kernel has total control, and so it can make it re-execute the sysenter, make it re-execute the syscall, make it re-execute the int instruction. So it just backs up the EIP or RIP, depending on what bit width you're at, and it forces the system call operation to run again. So it goes back to the process, and the process immediately says, I'd like to trap. And so it reruns the system call. I think this is pretty clever. Okay, any questions? So those are basically the details of how we deal with system calls. Okay. Now the last thing to discuss is this whole notion of jumping out of a signal handler, which seems crazy. Seems like skydiving without a parachute. Okay? So we can call siglongjmp to go to another part of the program. And remember that the whole point of this is you're terminating the signal handler, you're going somewhere else, because in response to the signal, you want to go and resume execution of something else. And it turns out that you can use longjump or siglongjmp. In fact, it's pretty wild. I don't know if any of you have read the documentation for longjump versus siglongjmp, but when you read them, they basically say, functionally, there's no difference between these two operations, except that siglongjmp may optionally restore the blocked and the blocked signal bit mask. Okay, that's crazy. And if you look at the implementations, that is exactly how they're implemented. Longjump and siglongjmp are identical, except that siglongjmp may optionally restore the block signal mask. It really depends on the arguments to sigsetjump. This is where you control that. Okay, so siglongjmp may or may not do that, depending on the arguments to sigsetjump. Okay. Now here's a question: does long jumping out of this signal handler, does it break the signal delivery mechanism at all? Okay, that's the question. And the answer becomes pretty obvious when you look at the idea behind jumping out of a signal handler and what would otherwise happen if you return from the signal handler normally. If you think about it, if you return from a signal handler normally, you are basically saying, I want the kernel to restore the machine context of the interrupted code, and I want to go back and finish what I was doing. If you long jump out of the signal handler, you're basically saying, I don't want to do what was interrupted by the signal handler. I want to go do something else. So you can imagine that you don't need to invoke sigReturn if you siglongjmp out of the signal handler, because the whole point of it is just restoring the process context. Okay, so recall. Let's see. Pending signal is dequeued. So this is referring back to a detail that I mentioned earlier. When we dequeue a pending signal, we basically say the signal is being taken care of. So no longer is there any detail saying it still needs to be delivered. So doSignal does that before it invokes the user handler. So it doesn't care what the user handler does. And it doesn't require the signal handler to return to complete processing, even in those system call circumstances. Because again, if we long jump away from that operation, our program is basically saying it doesn't care whether that system call finished or not. It just doesn't care. Okay? The kernel doesn't care. It should have been implemented properly to not need to go back to that. But basically, the kernel is indifferent. It's just absolutely, there's another word for it that I can't think of, but it's ambivalent about whether or not the signal handler goes back to the kernel or doesn't. It basically will only handle the situation where the signal handler goes back to the kernel if the process wants it. So it's again acting on behalf of the process. So, kernel always checks for pending signals to deliver when it's going back. So again, when a user process is scheduled, that's when we look at whether signals are pending. Okay? So if I jump out of the signal handler back to another part of the process, well, it will eventually block or be preempted or maybe terminate. In that case, we don't care. But if it blocks or is preempted, then we'll get to check whether another signal needs to be delivered, so that's fine. Okay. Also, the kernel stack is left untouched by this delivery mechanism. Okay. All of the state is on the user process stack, and if you think about what long jump does, it basically chops down the stack to where we actually care about, then it's perfectly fine to throw away all that data. We just don't even care. Okay. So like I say here, if we long jump out of a signal handler, nothing of value will be lost. Okay? If the process is designed to do that properly, then so be it. The kernel just doesn't care. Okay? And so this gets back to the other thing that I was mentioning, which is why would a process long jump out of the signal handler back to another part of the code? The reason why it does would simply be that it doesn't care about finishing what was interrupted. Because of the signal, whatever was going on, it just doesn't even care anymore about finishing that other stuff, which means we don't need the register state of the interrupted process. We really don't need any of this stuff anymore because we're saying, I don't care, I want to go back somewhere else. Okay? I don't care if the system call finished, any of that. So basically the long jump operation would throw away everything up to where the sigjump buffer says this is the state of the stack that I really care about. Okay? And in this specific circumstance, we don't care if sysreturn is invoked or not because we want to discard that state anyway. Okay? Everybody got that? Hopefully I belabored that enough and not too much. Okay, so that was signal handling in a nutshell, or in an hour-ish lecture. What we'll do next time is have the first of our 2 lectures on kernel memory allocators. Again, unfortunately, this is not something you get to explore in Pintos, which makes me sad because kernel allocation is the most important kind of allocation. It has to work really cleanly and without much fragmentation because, look, the kernel runs longer than anything else, and it needs to be fast because a slow allocator affects everything else. Okay? So we'll spend the next 2 lectures going through how kernel allocators work. Okay, so that's it.